A very good morning to all of you. So I cordially welcome you all for this engineering thermodynamics course. So the today's classroom discussion topics are Maxwell relations and TDS equations. So what is the importance of Maxwell relations and TDS equations? So that you are able to see in this particular the motivation. So it is important to know Maxwell relations and TDS equations. These are very useful to provide a way to exchange variables such as entropy, which is difficult to measure experimentally. Because I already told you that is the entropy is nothing but is the disorderness of the molecules. It is somewhat very difficult to measure experimentally. So getting the relationship between the specific heats, solving energy and enthalpy equations, the Maxwell and the TDS equations are very important one. So the outcome of the today's lecture is analyze the applications of Maxwell relations and the TDS equations. So here, just you go through this particular one. So is the Maxwell is the scientist. So he's born in Edinburgh in the Scotland. So he's a physicist, well known for his work in electromagnetism and field theory. Also known for his work in the thermodynamics and kinetic theory of the gases. So who actually derived this particular the Maxwell equations. And that is here the theory of the heat. That is a famous textbook which is written by the Maxwell. So it is published in 1870, describes its views of the limitations of the second law of thermodynamics. Maxwell relations were first introduced in this particular the theory of heat textbook. So why we have to use the Maxwell relationships? So why we have to study? So certain variables in thermodynamics are hard to measure experimentally, such as entropy. So Maxwell relations provide a way to exchange variables. So now just you go through the Maxwell equations. So here, actually whenever we are having the 8 important thermodynamic properties like pressure, volume, temperature, entropy, internal energy, H, Helmholtz function, that is the Gibbs function. So here, enthalpy, Helmholtz function and Gibbs function. So any one may be expressed as a function of any two others. So that's why for a pure substance undergoing an infinitesimal reversible process, so we can write down, because we know that TDS is equivalent to du plus PdV, and we can write down du is equivalent to TDS minus PdV. And here the dH, because you know that enthalpy is equivalent to U plus PV. So differentiate this particular one. So dH is equivalent to du plus PdV plus VdP. And you know that what we mean by the du plus PdV from this particular equation, it is nothing but the TDS. So TDS plus VdP. And you know that the Helmholtz function f is equivalent to u minus ts. So differentiate the Helmholtz function. So df is equivalent to du minus tds minus dt. And from this particular one, so TDS du minus TDS. So here in the third one, so du minus TDS is nothing but is minus PdV from the first one. Du minus TDS is equivalent to minus PdV. So minus PdV minus SDT. And similarly the Gibbs function, so G is equivalent to H minus Ts. So differentiate the Gibbs function. So dH value is equivalent to so and so. And we studied that. So how can we denote the thermodynamic property? That is, whenever a equation is given to you, so how can we say that it is a thermodynamic property or not? So let us say that a equation is there, that is a dz is equivalent to mdx plus ndy. So this particular equation can be known as a thermodynamic property if dou m by dou y with respect to x is equivalent to dou n by dou x with respect to y. So now just you apply all these particular equations to this particular one, that is just you correlate du is equivalent to TDS minus PdV, just you equate this equation to dz is equivalent to mdx plus ndy. That is here dz is equivalent to du and m is equivalent to t, dx is equivalent to ds and n is equivalent to minus p, dy is equivalent to dv. So like that just you equate the equation number 1 and this basic equation dz is equivalent to mdx plus ndy. So now what is the basic rule for the thermodynamic property? That is the dm by dy with respect to x is equivalent to dou n by dou x with respect to y. So now you substitute what are the values of m, y, x, n, x, y from this particular the first equation, so that you are able to get 11.4. Similarly, you equate the b equation with the dz equation, you will get 11.5. and the C equation with the dz equation you will get 11.6, and the D equation with the dz you will get 11.7. So these are known as the Maxwell equations. So these four are important Maxwell relations. So from these four important Maxwell relationships, we are able to derive the TDS equations. So that is, let us assume that entropy is a function of temperature and value. So then entropy can be written like this. So here the TDS value, that is from the Maxwell's third relation, we are able to obtain dou S by dou T with respect to T is equivalent to dou P by dou T with respect to V. It is a Maxwell third relation. So that is the same thing we are utilizing dou S by dou V with respect to T is equivalent to dou P by dou T with respect to Y. So whenever you are substituting this particular one in this equation, so we are able to have the first TDS equation, because basically we are having the two TDS equations. So the first TDS equation is given by 11.8, that is the TDS is equivalent to CV dt plus T into dou P by dou T with respect to V into dV. So it is the first TDS equation. And similarly here we assumed that entropy is a function of temperature and value. So now entropy is a function of temperature and pressure. It is the second assumption just you take. So ds can be written like this. Now here from the once again from the second TDS equation just you substitute. So now we are able to get the 11.9 is the TDS is equivalent to Cp dt minus T into dou V by dou T with respect to P into dou P. So this is the second TDS equation. So like this, in this class, we are able to derive the Maxwell relationships as well as the TDS equations, which are very, very important one. In the next class, we are going to discuss about the difference of heat capacities and the ratio of heat capacities. There we have to use this particular the Maxwell relations and TDS equations. So I hope the concept is very, very clear, because it is a mathematical derivations part only, the Maxwell relations as well as the TDS relationships. So the applications we will witness in the next class whenever we are dealing with the difference of heat capacities and the ratio of the heat capacities. So thank you very much for listening the topic on the Maxwell relations and TDS equations. Thank you.